NASA has announced 4 new payloads for Astrolab's first lunar rover, but most reports miss the real story. They list instruments like laser spectrometers or thermal sensors as separate items on a checklist. The reality is far more complex and critical. These 4 devices form a single unified system designed to solve the dust and power bottleneck that has stalled lunar exploration for decades. By watching this, you will understand how engineers are treating mobility not just as movement, but as an active survival mechanism against regolith contamination. The challenge begins with the environment itself. The lunar south pole is dark enough to trap volatiles in permanently shadowed regions, yet bright sunlight can bake exposed equipment. Dust there behaves nothing like terrestrial sand. It is sharp, electrostatically charged, and adheres to everything it touches. A standard rover design assumes that solar arrays will eventually get dirty but manageable. On the Moon, dust accumulation causes rapid power degradation because the particles form an insulating layer over photovoltaic cells while simultaneously grinding down mechanical joints. The result is a mission ending long before its fuel or batteries run out. The Astrolab approach changes this by integrating 4 distinct NASA payloads into one tightly coupled system, where each component dictates the constraints of every other. You have a laser spectroscopy unit designed to analyze regolith composition with high precision, but that instrument requires extreme thermal stability to function correctly. It cannot tolerate rapid temperature swings or excessive heat buildup during operation. Simultaneously, you need robust mobility systems capable of navigating rough terrain without getting stuck in the fine dust that clogs wheels and gears. Here is where the engineering becomes fascinating. The rover's mobility system acts as an active thermal management component rather than a passive transport mechanism. Engineers have designed the wheel assemblies to induce heat dissipation through friction during specific travel patterns. This means the rover does not just move to reach a destination, it moves to regulate its own temperature and clear dust from critical surfaces. Every meter traveled is calculated based on how much regolith needs to be dislodged from the chassis before thermal runaway can occur. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider the power distribution network that ties these systems together. The laser spectroscopy unit draws high instantaneous bursts of energy when firing its lasers at rock samples. In a standard design, this would require massive battery banks or complex voltage regulation circuits. Astrolab instead relies on the rover's own thermal mass to buffer these spikes. The system architecture treats the chassis as a heat sink that absorbs excess electrical load during operation and releases it slowly over time. This allows the laser to fire with high power without draining batteries instantly, but it creates a dependency between mobility speed and scientific duty cycles. The trade-offs in this design are stark. Production analysis reveals that mass and volume were optimized for a single integrated chassis rather than modular deployment. You cannot simply drop individual instruments onto the lunar surface because they would fail independently due to dust or thermal issues. The entire payload suite must move together as one unit to reach fresh regolith sites where conditions allow for safe operation. This prioritizes mobility over flexibility, forcing engineers to design a vehicle that carries all its science tools at once rather than deploying them sequentially. This integrated approach forces a specific operational rhythm known as the thermal recharge time. The rover's movement speed and stop duration are not calculated based on battery capacity alone, but on how long it takes for the payload suite to cool down after a high-power laser firing event. If the rover stops too quickly, heat builds up in the chassis faster than it can dissipate through wheel-induced airflow or surface contact. This creates a feedback loop where dust accumulation insulates the heat-generating payloads, leading to thermal runaway that forces early mission termination if the mobility system cannot physically dislodge the regolith blocking the cooling paths. The risk assessment for this payload suite identifies instrument failure as secondary to environmental interaction. The primary threat is not a broken laser or a dead sensor, but the cumulative effect of dust acting as an insulator on the rover's own heat-generating components. When dust builds up on the chassis, it traps internal heat from the power systems and instruments alike. This creates a self-reinforcing cycle where higher temperatures cause more thermal expansion, which alters wheel traction, leading to slower movement that reduces active cooling further. The system is designed so that if mobility slows below a critical threshold, the rover must execute an emergency clearing maneuver or risk permanent overheating of all four payloads simultaneously. Field tests on Earth have validated these concepts using regolith analogs for autonomous navigation and cargo transport systems similar to those being developed by European partners. These trials confirmed that wheel-induced heat dissipation is effective at removing loose dust from chassis surfaces during normal operation, but insufficient against the electrostatically charged particles found in lunar shadows. The solution required a shift from treating mobility as transportation to viewing it as an active cleaning and thermal regulation system. The unified engineering philosophy means that every decision about where the rover goes, how fast it moves, or when it stops is driven by the needs of all four instruments working together. A path selection algorithm does not just look for flat ground, it calculates which route will maximize dust clearance on solar arrays while maintaining thermal stability for the laser spectrometer during data collection phases. This creates a complex dance between scientific observation and mechanical survival that has never been attempted at this level of integration before. What makes this particularly significant is how it addresses the fundamental bottleneck of lunar exploration without requiring new launch vehicles or massive infrastructure changes. By optimizing existing technologies into a single cohesive system, NASA demonstrates that solving hard problems often requires rethinking how components interact rather than just building stronger individual parts. The rover becomes more than a vehicle. It becomes a mobile laboratory where movement and science are inextricably linked through shared power distribution and thermal dynamics. The implications extend beyond this specific mission. If the Astrolab design proves successful, it establishes a new paradigm for future robotic explorers operating in extreme environments where dust and temperature fluctuations pose existential threats to complex instrumentation. The ability to treat mobility as an active survival mechanism rather than just a means of transport could redefine how we approach long-duration missions on other worlds. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.